Then in the next chapter we will see U and V have a special name. They are called Hanger and Allenger matrices. But right now you just consider as two orthogonal matrices. And then we have U A V plus is equal to V transpose A plus U transpose. Can you tell me that, what is the meaning of orthogonal? What properties does it bring? It means that M transpose is equal to M inverse. M transpose is equal to M inverse. And I think now it solved it up, because if we have the plus, then it will be V plus, which is already V inverse, A plus U inverse, but we know that the inverse is equal to transpose. Why I am insisting to show it as transpose, because later in next chapter, as I said, when we are talking about the singular value decomposition, we have this type of notations, we want to use it. Now, proof, huh? In order to prove it, simply verify the expressions about satisfying P1 to P4. So very easy, right? I mean, we have to just verify a series of properties are okay. Another theorem that we need to also use it later in order to see how we can numerically calculate the A plus is this theorem, which you do not need to know about its proof at all. And the theorem is that let S belong to R n by n be a symmetric with U transpose SU is D, where U is orthogonal and D is diagonal. In other words, if you can find a U, that U inverse SU will result into a diagonal matrix. Because it is orthogonal, U transpose is the U inverse, right? Then S plus is U D plus U transpose, where okay, question. What can we say about D plus? We know that D is diagonal. What does it mean, diagonal matrix?
You only have elements in.
Yeah, I mean, we have only we have 0 for elements who are not on the main diagonal. I cannot say we don't have non-zero elements on main diagonal, because you can have any number on the main diagonal, 0 included. But definitely we have 0 if we are off the main diagonal, right? And we understand that everything here that we have is a square matrix, right? So where D plus is also diagonal, Now, D is diagonal, D plus is diagonal, and when we are multiplying them, what do I have to get?
D was?
D plus, or D plus D. If I do it, what do I get? I. So it means that when I'm multiplying them, everything is 0, that's cool, but we have only the main diagonal. So when I multiply them, these main diagonal elements should be multiplied to each other, which means that they have to result to 1. Can you tell me that how one number is multiplied by another number and it results into the 1?
Inverse.
Yeah, if they are inverse. Who is a diagonal and its elements are alpha inverse, which is 1 over alpha if alpha is not 0, and it is 0 if alpha is equal to 0. So D plus is also diagonal, whose element is 1 over of each of the elements that we have in D. This is very good because when we come to the concept of singular value decomposition, we have this notation, but the matrix which is produced in the decomposition, the middle matrix, is a diagonal matrix. So we use a combination of these two theorems in order to see how we can calculate the A plus. So do not forget these two theorems. What was it clear what's happening? I mean, lots of assumption. One then. So if S is not a square matrix, then we don't talk about this one. If U's are not orthogonal, then we don't talk about this one. And if all those conditions are satisfied, are supposed, then we can have S plus to be represented in that form. When you finish writing, let me know and I can. Another theorem, for all A belonging to R m by n, A plus is A transpose, A plus A transpose, which is A transpose A transpose plus, and A transpose pseudo inverse is equal to A pseudo inverse transpose. Check the proof on page 31. Note. What can I say about these two? Right? Hassan, what can I say about these two?
Generally, or
Let's start with generally.
It's like when we have the transpose, if the A transpose becomes A transpose B transpose.
What can I say? Right. If this is, let's say, equal to this one, this is not equal to this one. What is your feeling?
It's equal if they are orthogonal.
I don't think it's equal because
As Hassan said, let's write in general, and as Hassan said, they are not equal to each other. We can put lots of constraints and then come that they are equal to each other, and you can come with lots of examples which they are equal to each other, but in general, there is no obligation that they are equal to each other. Let's see. Let's see why. A is 0, 1, and B is 1 and 1. Please show that this is verified. I do the easy one. AB is equal to 1. So AB plus is 1 plus, which is 1. I want you to calculate B plus multiplied by A plus and show it to me that it is not equal to AB plus. Calculate B plus A plus.
why do we calculate B plus A plus? Should we calculate A plus B plus, or?
You should calculate first what is B plus, then you have to calculate what is A plus, and then you have to multiply it.
Yeah, I mean, here it says A plus B plus.
Doesn't matter, isn't it?
Okay.
I mean, you can say that AB plus is not equal to B plus A plus. There are dummy variables. You can say alpha, beta, or whatever.
Is it half?
Hmm?
Is it half?
It is half, so we want to come and solve it on the board. It's A transpose divided by. No, just put a transpose on top of A. Yes. Excellent. And thank you very much. Which easily we can see that AB plus is not equal to B plus A plus, because this was 1, this is 1 over 2. Actually, there is a theorem which you don't need to know it, but we can simply write it in parentheses. And the theorem says AB plus is equal to B plus A plus if and only if we have two conditions. One is the range of B transpose A transpose is a subvector space of range of A transpose, and two, range of A transpose A B. This linear transformation is a subspace of R B. But we don't care about this here. What we care more is this new theorem that we write. Actually, AB plus is equal to B1 plus A1 plus, where B1 is defined as A plus A B, and A1 is defined as A B B plus. Sorry, B1 plus. So first we have to calculate B1, and after that we can calculate A1. If A belongs to R N by R with rank R, and B belongs to R by M with rank R, then we have AB plus could be equal to B plus A plus. Which can be proved by this theorem, which I say is not important, so the proof of this is not important. Okay, we have another theorem, the last theorem for this chapter. For all A belonging to Rm by N, we have this. 1. A plus plus is equal to A. Two. Range of A plus is range of A transpose, which is range of A plus A, which is R transpose of A transpose A. And we can say the same thing for the null space of A plus, which is the null space of AA plus, which is the null space of A transpose plus, which is the null space of AA transpose, which is the null space of A transpose. And this theorem has the fourth step, which I write and I ask a question. Fourth one says, if A is normal, then A to the power of k multiplied by A plus is A plus multiplied by A to the power of k for all k belonging to n, and A power of k plus is equal to actually A plus power of k for all k belonging to n. And my question is that if R is equal to, my question is that what is the meaning of normal? You can finish writing and tell me that what was the meaning of being if A is normal? Hassan, what is A? What is the meaning of normal? What is the definition of normal?
Normal matrix.
Yes. Dana?
It was like R Hermitian multiplied by A to be equal to A multiplied by A Hermitian.
A belonging to R n by n is a normal. Because it's R, we just easily use the transpose. A transpose is equal to A transpose A. And it is good to know that given A belonging to R n by P and B belonging to R n by M, then range of B is a subset or a subvector space of range of A if and only if A plus B is equal to B. It's good to know it maybe one day you want it. Now, we said that in general, obtaining the A plus, if you remember from previous class when we geometrically show, is kind of a least square problem, right? And we wanted to find the point which has the minimum distance from all the intersections. Actually, in order to have a better estimation of or calculation of A plus, we have to use another method which is known as a singular value decomposition. Of course, singular value decomposition is not only defined in order to calculate your A plus. It has lots of cool features, cool properties, which we will talk about them. So our next chapter is an introduction to singular value decomposition. We will talk about what is singular value, how do we decompose it, what are the properties it has, and then as an example we will use those two theorems which I discussed and said that we will use them in the next chapter in order to solve a numerical example for calculating A plus. And this is actually how MATLAB calculates A plus. Now, do you have any question? So odd or evens? I mean, democracy. Odd or even?
How many questions?
I have no idea. That's why I said odd or even. Odd. Odd. It doesn't matter what you say. Majority voting odd. So odd questions will be your homework. Give me your pen. I will upload them. So this means that definitely the pseudo inverse is included in our midterm examination. And on Friday, we will start to talk about singular value decomposition. Whether singular value decomposition is included in the midterm or not depends on how far we are going. Because as I said, one session before the midterm, when is our midterm?
26th.
26, which means
2 weeks from today.
2 weeks from today. Because before it's on Friday, right?
No, it's on Wednesday.
On Wednesday. Which means that on the next Friday, I will do some problem solving. So what if I manage to finish the singular value decomposition by next Wednesday, it means it will be included in our examination.
We have 2 classes before the exam.
No, we have 3 classes before the exam.
Classes. Oh, 3 classes.
Yeah. Which theoretically we can finish the introduction to singular value decomposition, and I can have one practical, tutorial for you. So with high probability the next chapter is included, but we will decide on that one on next Wednesday. All right? Do you have any question? Okay, you may stop the video, Dana.